Okay, so Robbie Knievel is going to jump the canyon, but here's the kicker. His landing point is below the takeoff point. It has to be. Why? Yeah, even if he jumps off a ramp and is directed slightly upwards, he's going to lose energy as he travels across. You're not going to jump lightly to a higher point on the other side. The smart thing to do would be to jump from the high side to the low side. You stand a better chance of not, landing right into the side of the canyon on the other side, because you get this advantage of being above where you started. All right, so he's going to jump like this, but the challenge is he has no speedometer because he's on a dirt bike. Okay, he can't see his landing point because he's way above it, and there's a ramp in front of him, so he won't even see the landing point until he's already in the air. Okay, and then he's got to stick the landing, which is like falling a long way. Okay, several meters, kind of like if you or I were to ride a bike off the top of the gym. Okay, sticking that landing would be somewhat difficult. This is worse than that. He's going way faster than we would be. Okay, so he's got to stick the landing, and for some reason he doesn't have a really long landing area. He's got a really long takeoff area. You got to build up speed to make it across, but who cares? Once you get across, everything will take care of itself. It'll be fine. Yeah, but it won't. Oh, I gotta pause the recording, otherwise I'll get a copyright violation. All right, so I want to see how much you remember from last year with your roller coaster questions and what we talked about yesterday. Okay, and I want you to see if, given that situation, right, knowing that the speed he left at was 38 meters per second, okay, the height was 70 meters, how fast was he going when he hit the ramp on the other side, 35 meters below where he took off? Okay, so all of these heights are measured from the bottom of the canyon. Okay, so he takes off 70 meters above the bottom, and he lands 35 meters above the bottom. His takeoff speed is 38 meters per second. I want you to calculate how fast he's going when he hits the ground over here using what we learned yesterday about the law of conservation of mechanical energy. Okay, so I'm just going to spread this out a little bit so that you can see where else this is going. How do we calculate mechanical energy? EP plus EK. It's the sum of your potential energy and your kinetic energy. Okay, do we have formulas that calculate each one of those things? All right, and what we're looking for, the final speed, is part of which term? Which kinetic? The final. Okay, so what we're looking for is part of that term. Okay, let's see if you guys can take it from there, and then we'll work it out together after. Okay, according to the law of conservation of energy, in the perfect physical world, the amount of mechanical energy that he has here on the high point is the same as the amount of mechanical energy that he has here. That's why we wrote EI equals EF. Okay? There's not going to be any loss to friction or air resistance or anything like that. We're saying all of it is conserved. Okay? So that means his mechanical energy, potential and kinetic, here is equal to his potential and kinetic here. Now, what I'm looking for is part of the kinetic energy. So what I'm going to do is isolate this term before I plug in the rest of the formulas. It's one less thing I have to do when I got all the variables in there. Okay? So how do I get EPF over to the other side? Just subtract. Okay, so I'm going to have EP initial plus EK initial minus EP final equals EK final. All right, now I'm going to plug in all the formulas, okay? Because now I've done as much as I can to this point with these. All right, so I calculate potential energy by going M times G times H initial plus 1/2 times M times V initial squared minus M times G times H final. that will equal 1/2 mv final squared. All right, what I'm looking for is v final, vf. So I have to move a half and an m. How do I do that? Divide them over to the other side. Okay. Even before I do that, let's say that before I do that, what variable is in every term? Mass. That means everything is being multiplied by the same number. What can I do with it? Cancel it. That's why it doesn't matter what it is. It's in every term. So I can just do this, and it doesn't have any effect on the end result because it's in every term. Okay? So I'm taking it out. Then I'm just going to divide by 1/2. So I've eliminated the m's. Now that gets me vf squared. I want vf, so I have to square root it all. Okay. So when I plug in my numbers, what I'm looking at is 9.81 times 70, so g times my initial height, plus 1/2 times 38 squared, the initial speed, minus 9.81 times 35, final height, divided by 1/2. Okay, so when I'm punching all this in, I wouldn't recommend trying to punch it all in at this, like in brackets underneath the square root sign. You're just inevitably going to make some small mistake somewhere. Okay, so I'm just going to go 9.81 times 70, okay, plus 0.5 times 38 squared, minus 9.81 times 35, divided by 1/2. Then I'll square root that. All right, so when Robbie Knievel hit the ramp on the other side, he was moving at 46.1 or 46.2 meters per second on the other side. Okay, assuming all of his energy was conserved. All right, to give you an idea, that's 166 kilometers an hour. And you can see why he got the speed wobbles, okay, almost immediately after landing. Okay? If you've ever ridden a motorcycle, you know, maybe know what the speed wobbles are. Okay, so people get going really fast, and even the slightest thing changes, they correct for it, and then they overcorrect, and they just start to wobble, and then they go down. Yeah. All right, that looked familiar from last year. Okay, we would have done roller coaster questions work exactly the same way. Okay, but they all the law of conservation of energy questions work just like this. We set initial equal to final, we manipulate for whatever it is we're looking for, and solve. There's really not much to them other than being able to tell them apart from a work energy theorem question, because they do give you a lot of the same information. So being able to tell them apart is important. Okay, here's how you tell them apart. A work energy theorem, or sorry, a law of conservation of energy question will never give you force. Okay, you will never get force in a law of conservation of energy question, because that would imply work is being done. And in a conservation of energy question, there's no change in energy. The initial and the final are equal, so no work is being done in those kinds of questions. Okay. The other thing to look for is key words like work, okay, or change in energy. If there's anything about changing energy, forces, or work, it's not this kind of question. Okay, this kind of question won't ever mention any of that stuff. Okay, so that's what we did. Okay, that's just the nicely typewritten part of it. Right. So we're going to look at a few examples here. So we got a frictionless roller coaster that it has a mass of 800 kilograms, which we may or may not need. Okay? At one point on its journey, the car has a speed of 4 meters per second and is 35 meters above the ground. Later, its speed is measured to be 20 meters per second. Okay? It's asking us to do two things. Calculate its total initial mechanical energy and find its gravitational potential energy, not its height, okay? Just its gravitational potential energy in the second position. All right, so this is what you're starting out with. Okay. 35 meters, okay, 4 meters per second. Okay, a little while later, it's moving at 20 meters per second. How did I know to put the second point lower than the first? It has a higher velocity. Yeah, if energy is being conserved, the only way I can be going faster is if I've turned some of my potential energy into kinetic. Okay, that's the only place I get energy from because they're equal. Okay, so the only way I can be going faster is if I'm lower. So I want you guys to calculate the total initial mechanical energy and then calculate the gravitational potential energy in the second position. Okay? As a hint, you will need the answer from the first part to do the second part. How do we calculate mechanical energy? Nope. I just want to calculate mechanical energy. I add two things together. What are they? Kinetic and potential energy. Okay, so they want me to calculate the initial mechanical energy, which, spoiler alert, is the mechanical energy anywhere along here because energy is being conserved. Right? Doesn't change. So I just need to calculate how much mechanical energy is present here because this is where I have the information to calculate that number. I don't have it anywhere else. So mechanical energy equals EK plus EP, right? Which is what we were doing in the last problem. We just had it as part of something else. Okay, so I know the mass and I know the speed here at the beginning, so I can calculate the kinetic energy. And I know the acceleration due to gravity and the height at the beginning. So all I have to do is plug in my numbers. 0.5 times 800 times 4 squared plus 800 times 9.81 times 35. Okay, so there's my mechanical energy. They're calling it the initial, but because there's no energy being lost anywhere, that's actually my mechanical energy anywhere along that roller coaster's track. Okay. All right, 281,080 joules. Okay. The second thing they want me to calculate is the gravitational potential energy in the second point. So here's where what I said about the track becomes important. This number is the amount of mechanical energy here, 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 and there, anywhere along that track. That is the mechanical energy. And mechanical energy is always calculated with this formula. They want me to calculate the final potential energy. I know this number already. I might be able to calculate this one so I can get that. I'll give you a couple minutes. Okay, so this number is the mechanical energy here at the bottom, okay, and it equals the kinetic energy at this point plus the potential energy at this point. And I have enough information to calculate the kinetic energy at this point because I know it's moving at 20 meters per second here. Okay? So my next step then is to say the mechanical energy final, which I already know is 281,080 joules, equals 1/2 mvf squared, okay, plus my final potential energy. They want me to calculate this number. So I'm going to move this over to the other side. And I'm going to have 281,080 joules minus 1/2 times 800 times 20 squared. That will equal my final potential energy. Okay, so when I do that, I get that there's 121,080 joules worth of potential energy at that point. All right, follow-up. How far above the ground is the roller coaster at that point? Okay, so I've just calculated that this is my potential energy. Okay. Do I have a way to use that number to calculate the height of the roller coaster? Okay, I give you one more minute. I think that's all it'll take you. So this number that I just calculated, 121,080 joules, equals m times g times h final, because it's the potential energy at the end. Okay, all I have to do is divide both sides by 800 times 9.81. That'll give me my final height. 15.4 meters. Why didn't I cancel the masses in this question? Well, A, I had the mass, but also they were asking me to calculate the energy to start, and mass is part of that. If I'm just being asked to calculate a height or a speed, mass doesn't affect those things, so mass can cancel. Okay? But if I'm being asked to calculate an energy, and I don't include mass, I don't get kilogram meters squared per second squared, which is a joule, if I don't have the kilograms in there. Okay? But if I'm calculating a speed or a height that's not dependent on mass, then I don't need the mass. Does that sort of make sense? All right. Okay, I want you guys to try 1 and 2 here. I'm going to make them bigger so you can actually read them. Okay, if it says in an isolated system, it's telling you it's a law of conservation of energy question, because in an isolated system, you can't lose energy to work, to non-conserved forces. Okay, and then in number 2, they actually say use conservation of energy to do this, so that they're telling you these are both conservation of energy problems. Right? So I'm going to give you a bit of time on those. These are not so much mathematical as they are testing your understanding. Yes. So on number 1, they've got this crate that is sliding down a frictionless ramp. Okay, since it's frictionless, then it can't lose any energy, okay, to any non-conservative forces. So it starts up here, and up here it's got 250 joules of kinetic energy, and it's got 960 joules worth of potential energy. Now it says it loses 650 joules of gravitational potential energy. What happens to potential energy as something slides down a ramp? It's not lost, it's turned into kinetic energy. Okay, so what do I do with this 650 if I want to find the kinetic energy? Not subtract, add it. Okay, if this is the amount of potential energy lost, it's the amount of kinetic energy gained. Okay, so I take this 650, I add it to the 250, and I get that there's 900 joules of kinetic energy at the bottom. Okay, or at the other, it's not, I guess, at the bottom, but close to the bottom. Okay, That makes sense to everybody? All that one is asking is, do you understand energy is conserved, so any potential energy that disappears doesn't disappear, it becomes kinetic instead, okay? They're turning into each other in a conservation situation. All right, so give number 2 a try here. Okay, we got a 55 kilogram mass, it's 225 meters above the ground, moving at 36 meters per second, and we're trying to use conservation of energy to calculate its velocity when it reaches a height of 115 meters above the ground. So it's actually moving upwards, okay, which is fine. It's just going to go higher and faster or slower? Slower, right? Okay, so it's an EI equals EF question. See if you can solve for how fast it's going when it's 115 meters above the ground. Okay, let's have a look at this one. So sorry, I misread it. I thought it said it was at 25 meters. Okay, so this is actually falling. It starts at a high point and moves to a low point. Okay, so we have the initial point being 225 meters above ground level, and it's falling to a height of 115 meters above ground level. Okay, and we know its mass as well as its initial speed. At that 225 meters, it's traveling at 36 meters per second. So the initial mechanical energy is going to equal the final mechanical energy. Okay? Then what I have to decide is what kinds of energy does it have initially? Well, it's 225 meters off the ground, so it's got initial potential. It's moving at 36 meters per second, so it's got initial kinetic. Okay? And at the end, it's 115 meters off the ground, so it still has potential, and it's got to be moving, so it's also got final kinetic. They are, after all, asking me how fast is it going. I can only assume that number won't be 0. Okay? All right, so what I am looking for is part of this term here. So what should I do with EPF right now? Subtract it over to the other side. Okay, so EP initial plus EK initial, okay, minus EP final equals EK final. All right, this is just like the one we did before. Okay, from there, now I can put in all my formulas. M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals 1/2 MV final squared. All right, they told me the mass. Do I need it? No. I can cancel it out and really reduce the amount of chances for mistakes, okay? And I'm going to do that. You don't have to. You can leave it in there and punch in 55 4 times, okay? Totally up to you. It won't change your answer as long as you don't mess it up when you're typing it in, which is my fear, which is why I'm taking it out, okay? All right, I want to calculate VF, so I need to move the 1/2 over to this side by dividing both sides by it, and then I need to take the square root in order to get VF not squared. So now, when I plug in my numbers, okay, 9.81 times 225 plus 1/2 times 36 squared, so there's my initial potential, my initial kinetic, minus my final potential, 9.81 times 115, divided by 1/2, all square rooted, okay, should give me my final speed. Okay, so we got 9.81 times 225 plus 0.5 times 36 squared minus 9.81 times 115 divided by 1/2, okay, square rooted. All right, well that makes sense. It should be going faster. It's falling, okay? Moving at 58.8 meters per second at the second position. All right, everybody follow what I did there? Okay. Now, number 3 is a real thinker. Okay? I would never ask you to do one like this on a test. Okay? When we used to have the IB program, which is now from the AP program, we used to have Physics 20 IB. This would have been an exam question. Okay, it's tough. Right? But it's not beyond your ability to do. It's law of conservation of energy with the tiniest little bit of projectile motion thrown in. Okay, projectile motion is what we did at the very end of the first unit. Okay, so a little bit of that comes into play here for the human cannonball. All right, so what we know is that the human cannonball is fired at 21 meters per second at an angle of 20 degrees above the horizontal. Okay, so we know their initial speed is 21 meters per second. We know that this is their initial height. Okay, they are looking for the gravitational potential energy relative to the ground when he is at the highest point in his flight. Okay, and then for part B, they want to know how fast he's traveling when he hits the net. Right? You could actually do part B without doing part A. Part B you guys should have no problem with because it doesn't involve using projectile motion at all. Okay, it's just law of conservation of energy to figure out the part B. Okay, but for part A, you will have to do ever so slightly small amount of projectile motion. All right, give you guys a few minutes on that one. Do part B first. We'll go over part B. Then you can work on part A. Just as a question, does the angle matter if you're doing law of conservation of energy? No, it doesn't. Okay, remember, energy is scalar. All that matters is how fast you're going, not what direction. Okay? That angle is only there for part A. Okay, so for part B, it's just a law of conservation of energy question. The initial mechanical energy, where he's launched, is equal to the final mechanical energy when they hit the mat or the net, okay, at the bottom. All right, so at the beginning, he's 15 meters above the ground and is moving at 21 meters per second. Whoops, that's not final, it's initial. Okay, so they have both kinetic and potential energy initially. And they have both kinds at the end because obviously he's still moving at the end and it says that he's still 2 meters above the ground. So there's some potential and a lot more kinetic. Okay, what I'm looking for is part of the final kinetic, so this is exactly the same manipulation we've been doing all along. Okay, I want to bring EPF over here, so I'll have EP initial plus EK initial minus EP final equals EK final. And then when I plug in all my numbers, MGHI plus 1/2 MVI squared minus MGHF equals 1/2 MVF squared. Okay. I'm looking for VF. I don't need M because it's in every term, so I'm going to get rid of it. I'm going to divide both sides by 1/2 and square root, just like we did on all the other ones. Okay, so VF will equal 9.81 times 15, my initial height, plus 1/2 times 21 squared, the initial speed, minus 9.81 times 2, the final height, divided by 1/2. So we're looking at a speed of 26.4 meters per second when they hit the ground, or hit the net, not the ground. Because it's going a little faster if they hit the ground, because they'll fall another 2 meters. All right, everybody okay with that one? Yes? Okay. Now, the mechanical energy at any point is the same, yes? Beginning, end, or anywhere through the flight. So, I should be able to calculate the maximum height, okay, and thus the gravitational potential energy. But there's a quicker way to do it, and that is using some projectile motion. Okay, so what we're looking at here is this situation. Launched at 21 meters per second, 20 degrees above the horizontal. Okay. That number has a horizontal component and it has a vertical component. Now, when they get to their highest point, how fast are they moving vertically? 0. But their horizontal velocity never changes. So if I use projectile motion, I can calculate how fast they're going at the highest point, because at the highest point, they'll still be moving horizontally. Okay? That will be where all their kinetic energy is. Once I have that number, then I can work backwards and find out how much gravitational potential energy they have. Okay? Everybody with me there? I'm going to let you run with that and see if you can get it. Okay? You will have to do another energy calculation as well, because I canceled all the m's when I did part B, and I did that on purpose, so that you would get the actual number, okay, for the mechanical energy. So you will have to calculate that as well. Okay, give you a few minutes on that. See how much projectile motion stuff you remember. This is your midterm right here. I don't believe in midterms, so see if you remember your projectile motion. So the reasoning here is that when this human cannonball is at the highest point, okay, all of their velocity is horizontal. And I can calculate what that horizontal velocity is using projectile motion, because it'll be the horizontal component of their launched speed of 21 meters per second. Okay? So what I'm going to do is calculate V horizontal here and know that that will be VF at this position. I'll still use this as my initial position because I have all the information for it, and then I'll be able to use this to get my final kinetic energy, and then I can solve for the final potential. Okay? So I'm just going to go cos of 20 times 21, and that'll give me my speed right there. So that's the projectile motion part that we had to remember. So cos of 20 times 21, okay, is 19.73 meters per second. All right, now that I have that, now I'm going to go back to this. Law of conservation of energy. All right, so my initial is going to be m times g times h initial plus 1/2 mv initial squared equals mgh final, and I'm actually not going to write it that way. I'm going to write it this way because that's what they want me to find, okay? Plus 1/2 mvf squared. So I want to find this, so I'm going to move the 1/2 mvf squared over here by doing what? Subtracting, right? I'm bringing the kinetic energy over to this side so that I can solve for the potential, okay? Because we know it's potential plus kinetic equals potential plus kinetic. All right, I'm also going to take out all the m's. Actually, no, I'm not. I have to leave the m's in because I'm finding energy. Okay, so I'm going to leave the m's in. M times g times hi plus 1/2 mvi squared minus 1/2 mvf squared equals my final potential energy. So now I just have to plug in my numbers. So that'll be 56 kilograms. So 56 times 9.81 times 15 meters. That was the initial height. Okay, plus 1/2 times 21, or sorry, times 56 times 21 squared minus 1/2 times 56 times 19.73 squared. Okay, that will give me my final potential energy. So 9.8, sorry, keep forgetting the mass. 56 times 9.81 times 15 plus 0.5 times 56 times 21 squared minus 0.5 times 56 times my answer squared equals. All right, so there's the gravitational potential energy at the highest point. Could I also now calculate the highest point? Yes. Okay, all I'd have to do is divide this by 56 times 9.81 because that's potential energy there. Just dividing by mg, right? So they only end up being 2.6 meters above where they're launched from, but they're launched at a very shallow angle, so that makes sense. okay? I would never ask you to do one that involved. I might ask you to do something like B, okay? But I wouldn't ask you to do something like A on a test. Now, something that does come up on a test sometimes is this. At the beginning of this question, I asked you, does the angle matter for conservation of energy? And you guys answered correctly. You said, no, it doesn't. Okay? And then I said, that's right, because speed and energy are scalar quantities. Okay, so if I'm flying along in an airplane, okay, flying along at, let's say, 150 meters per second, but I'm flying horizontally, okay? If I jump out of the plane, do I have kinetic energy the instant I jump out? Yes, I do, okay? And why do I have kinetic energy? I'm not moving vertically, am I? When I first jump out of the plane, I'm not moving vertically, but I'm moving horizontally, okay? I would have the same speed as the plane, right? In fact, if it was a perfect physical world, me and the plane I would fall, but the plane would stay up, but I would move right along with the plane, okay? When I finally got to the ground, my parachute didn't open, okay? I would hit the ground directly below the plane. Strange but true, okay? But people forget that. As soon as I put it in a context like that, they're like, oh, well, he jumped out of the plane, he wasn't moving. Yes, I am. I'm moving at the same speed as the plane, and I do have kinetic energy at the beginning. So it's something to keep in mind. Sometimes people don't catch all the stuff in the context of the question.